Just
Really?
yeah.
Dude. I sound like actually.
Yeah. I don't know.
I don't know how was I next. I parroted all of them.
I did a several ones did. It goes on some. That's what's going to happen.
On the board is today's attendance question. It's a moment generating function. So we wish to be able to determine the moment of the function when the moment generating given. So to answer this question, we really need to know what moment generating function is used for. What you're gonna do is you find the derivative, and then you make t equal to 0. You find the first moment, you find the first derivative, and then make t equal to 0 to calculate the first moment. And then you find the second derivative from the first derivative. You can make the t equal to 0 again to find the second moment. That will be the expectation of x squared. The variance of the function equal to expectation of x squared minus the square of the expectation. Then subtract the two. You'll be able to determine the variance. Standard deviation is the root of the x. Let's try it. you figure out the answer? The answer for the, did you email me?
The one that I was struggling with.
Yeah.
I haven't checked my email to see what your reply was yet, but
Oh, no. I answered that we're gonna do it together in class. I thought if you figure it out before class, then we don't have to come, but I think it's a common problem, but. Last week I skipped it because I was like, how do I do it? I feel like I have the answer, but I think it's the conditional probability that's what's making it. So you figured out the first answer already.
yeah, I had part 1 and part 3 done. It was part 2. As said, I tried to calculate it like several different ways. Some of them gave the same answer. One of them was an answer I was fairly certain was wrong. But then also while I was entering my answers, I kept missing like,
Uh-huh.
but I was just expanding it out. So I missed the parentheses and this spreads. Something.
You guys have the answer yet? Okay, let me see. So we need to know the derivative. For example, the first derivative is equal to 0.45 multiplied by this 0.35 e to the 2t derivative is 2 times, so it's 1 to e to the 2t. And then 0.15 multiplied by 3 and time e to the 3t, t minus 1. The last one is 0.05 times 4, and then e to the power of 4t. Right, that's the first derivative, and we wish to find the f prime 0 because that will be the exponential, the expectation of x. Okay, and then in that function, if we make t equal to 0, that e to the t equal to 0 will be 1, so that condition 0.45 plus 0.7. 0.45 again, 0.2. And that's 1.8. Okay, so then we also have to find the expectation of x squared. For that, we need a second derivative, which is the derivative of the first derivative. That again is 0.45 e to the power t plus, you have to time another 2. So it's 1.4 to the power of 2t. That's the temperature, the third term times another 3. What is it? 1.35 e to the 3t. 1, 2, 3, fourth one times another 4. Is 0.8 e to the 14. And then to find the expectation of x squared, we would make the t equal to 0 in the second derivative of long-term function. That's the all right. When we do that, it looks like 0.45 plus 1.4 plus 1.35 plus 0.8, which is, what is it? 4. Okay. So then there is basically equal to subtraction 4 minus 1.8 squared. That's the variance, right?
So
0.76. And then we take square roots, that will give us standard deviation. Okay. Just want to use that example to give us 15. How do we determine the standard deviation using the moment? Weird. Let me try again. It didn't go through. Is it? Okay, that will be today's attendance. Do you have any questions? Oh. Sorry. I think we already. Okay, did you scan?
Yeah.
Let me scan it again. No, that's this one. Right, okay. It should be B. Do you have any question? Okay, so it should be the square root of 0.76. So it's B. This is a process for the calculation. I write the exponent because I was typing. That's how I was writing the exponential function there. Now, I want to go through this one. The question number 1 on the homework 2.6. If you have any question, then we will go through it. The first question is trying to figure out the conditional probability. It says if she arrives home without the icon and she doesn't know which class she left it. What is the probability she left it in the 5th class? So it will be a conditional probability. I mean, if you have already finished it, then this will be something extra. So the first question will be it's a conditional probability. The denominator will be she arrived home without the paper. So it could be that's according to 0.25. So 0.25 probably left it in the 1st class. And then maybe or plus she left it in the 2nd class, so 0.75, 3/4. She didn't left in the 1st class. And then she left in the 2nd class, the probability left it there. And then or so I do summation because it's the or relation, or maybe 0.75. Didn't left the 1st one or the 2nd one. She left it in the 3rd class. So raised to the power 2 and then multiply by 0.25. That's the 3rd class that she left it, and then or the 0.75 now in this first 3 class. In the 4th class, that's where she left the clicker, and then lastly 0.75. Not in the first 4 class, in the 5th class she left it. Okay, and that should be basically the denominator, right? Is that how you calculated?
I calculated it that way once, and I also did 1 minus the probability that she didn't leave it.
Oh, that will be
1 minus 0.75 to the 5th.
right. That will be this will be one way. The other way will be 1 minus the probability.
So I did that both ways, and then I just had the
That should be the same answer.
yeah, and then I had the top the
This will be
0.75 to
the
the 4th times 0.25.
right. This will be the top.
I don't remember if that's the one it kept telling me I was wrong, but that's what my answer was. At least on
We have to round it to 3 decimals after we get the answer. Right? The first question was okay. And then so those will be the answer for the first question. And then after you calculate it, you round it. The last question is,
Can you
she
scroll
arrived
back up?
home? Yes,
Scroll back up just a second.
okay.
Thank you.
So
You're good.
okay, so the last question is she arrived home and didn't have her eye clicker, and also she's sure she hasn't clicked her after leaving the first class. So obviously there's it's not gonna happen to be that case. So she didn't left in the first class, right? She's sure she had it. So then the probability for so the denominator is a condition, right? She already know it's not, she didn't left in the first class, so we take out that 0.25. And we still try to find the probability that, that she left in the fifth class. So probably left in the fifth class will be not in the first four class, in the fifth class, so right, the numerator will be that. But denominator should be everything that has that has already been no clicker. That means 0.75 to the power 5 is not in the denominator. But you're gonna have to take that one out because she's sure she didn't left it there. So that's probably for leaving the eye clicker in the first classroom, right? So without that part, everything else, calculated and divided should be the probability for the last part. Are we okay? Wait, is that okay? All right. And then the second question is asking, what's the second question? Or space. She arrived home with without the eye clicker retrospectively. Okay, she has enough time to get to only one lecture signature for the signature of them. So if she only have one chance to go to one classroom, she goes to the one that has highest probability. So we would try to compare all these chances. Probably she left in the first classroom, probably she left in the second classroom, probably she left in the third classroom, fourth classroom, and fifth classroom. All five you calculate it, whichever is bigger, that's the classroom she should go first, right? So if you compare all of this probability, if you multiply all together, I think the highest one is the first one. 2.25 is bigger than all the other number. So she should go to the first classroom should get it because it's a higher chance that's what happened. That's the classroom she left. Any question? That's
I'm looking at it,
I see.
if she's sure she.
Oh, I think it's the wrong thing. It says 1, 2. Three significant figure. So after you got your final number, you wanted to link 104. Let's see. I think it doesn't. This question in particular doesn't want any formula. So you finish your calculation. Okay. What is the probability she will leave in this class? Oh, it's a numerature. So this is not conditional probability. Those we have to do division because we said if this is happen, what is probably that? So I have to do a division because it was a conditional probability. Now yours is a pure what is probability she left it in this class. That means the first four class you didn't leave it there. So it's 0.75, 0.75 for the first four, and then 0.25 for the last one. So it should be like 0.75 to the power 4 and 0.25. That's the number. And then you have to round it to if you want to. Once you find the answer, you round it to. Yes. Yes.
So your part here was this.
Yeah. So if it's conditional probability, we do it differently. If there's no additional, and there's no condition, there's no if, then it's just the probability of that situation. Any other question? I can look at your version. It looks like it's being randomized. We're not getting the same question. Do you have any question? All right, so hope now we can finish this one. So it looks like we all are getting a slightly different version of the same question. Any other homework question? Were you able to finish this one? Number 1? 6. Okay. All right, you all know that this Wednesday we have our first test. Do you have any question? Or yes,
Would the topics covered on the test be the same topics covered in the test group?
yes.
Because I noticed like, some of the sections were not like that prevalent in the,
Yeah,
but that's a, like, you don't have to worry about those.
right. So you can download those test one study.
Even that shit
Yeah.
sounded good.
Like the first question will be one of the probability. You have to apply the addition rule for probability. Maybe having a Venn diagram. So that would be the first question. Focus on
30 different
addition rule.
calculations. Those tips without
The yes. What's that? I think it's all
So it would be good.
weird in the weird order. It was this one. Isn't that the one?
That's the- We'll focus your bets.
That's the one we just did, right?
That's
It
about
was
where-
answer for. That what is. It's the example that we just using. Okay, so anyway, so moving on, this is question 1, this is question 2. The question 2, I think I didn't really copy the question in here. It was a moment generating question, right? So there will be one question with moment generating question 1, question 2. And question 3 is one that has multiplication rule. So we have, and this is also could be answered with the hypergeometric distribution if you look at it. Any question? So that was a hypergeometric distribution. We use a combination number to find the universal denominator. And this is one of the question that we have to apply Bayes rule. And that was a calculation for the full probability. It could also be a Bayes rule where it's a additional probability is being calculated. Any question for number 4? And then number 5 is the part with the table. So it's a chapter 1 question when the contingency table is provided. We should be able to calculate conditional probability from the table. And that will be one of the questions related to the homework. Number 6 is a Poisson distribution question. And I suppose you should be able to solve any question from the Poisson distribution homework. So it's not this question, it might be any of those Poisson distribution homework questions. So make sure you understand the homework. Number 7 is another example where the Bayes rule is being applied. Bayes homework. Number 8 is the combination number. It's from section 1.2. About enumeration, combination number or permutation number. And then there's number 10. That was calculating expected value when you have a gain or some kind of distribution that we can find. So this is one of the questions from section 2.1 for calculating expectation. This is the calculating expectation and they're from a table. So it's different than the moment generating function, also different from the section 1. Okay, this is the binomial distribution question. This is the Poisson distribution question. And then that's the moment generating question again. Like basically 2 Poisson, 2 moment generating function, 2 calculation of exponent and variance. Yeah, that should be all 14 questions.
And how would you like this, how are we expecting that? Are we
Right.
expect, yes, that'd
Yeah, let's 2 decimal, 3 decimal. If the number is really, really small, of course, so we have to go more decimal. If the number are just average number, then 2 decimal, 3 decimal. Okay.
Yeah.
Any other question? This is already online. I hope you had a chance to look at it. So that's basically the plan for the first test. If there's no other question, I'll continue with 3.1 then. Any question? Yes.
She originally, so basically given that she left it, she left it in the fifth class. So that should be probability she left it in the fifth class overall over just the number of years to leave it. So that should be this.
Yes.
It always tells me I'm wrong.
I guess it's like long. Can you round to 3 decimal, like 0.116? Okay,
Then it's enters in seven different ways.
the denominator, have you tried to enter it?
I've tried to earn it by doing the probability she
Summation?
left it in the probability. she
Have
left
you
it in the fifth.
the summation? So,
Yeah, then probability of she left it in the first, she left it in the second, she left it in the third, she left it in the fourth, she left it in
Right.
the fifth. So I entered it that way, which was still 0.116.
is it?
Entered that way.
Let me try to enter it. Let's see, so 0.25. Let's try to make it larger. Left in the first classroom. Left in the second classroom. Third classroom. Times 0.25 left in the fourth classroom. You guys think these. So I think this may not be 0.116.
Well, that's not gonna be 0.116, but the probability, like, it'll be the denominator. And then,
This is the denominator.
Yeah.
Yeah, so
and then you'll have that,
this is in the denominator and the numerator would be this one. Okay, and then this will give us a. So I have 0.104 instead of, so 0.104 instead. I can
I'm
also
pretty sure it'll
try.
also be. that.
That should be right. That's what I put in. I
It-
put
It's a
0.1.
0.14. As I said, I've entered it that way.
If it's 0.75 to
Oh,
5, let me see,
That's it, we're good. It went through that.
okay,
That's what it popped up. I think
yeah,
it was 0.0.
it's the same,
0.103 something, something, something when I entered it in, the whole summation,
Yeah.
but it still told me it was wrong one time when I entered it in
I
that
think
way.
it's
So I
how we entered it, I don't know.
yeah,
So this is why I separated numerator and denominator. I calculated whole denominator and then calculate the numerator divided by the denominator. Maybe when we try to enter the fractions, something happened.
maybe.
So maybe we did numerator and denominator separately. It was.
Yeah, I mean, I could have also had like rather than having a caret, I might have missed the caret at 0.755 and then it threw it off by enough down the road that it
Yeah.
considered it incorrect.
Any other question or concern for the test? You can bring an index card for your formulas. You can use your
I'm a
calculator.
different.
You can write on the test paper, try to present your steps and calculation to get partial credit. We're all in the higher level math class. I guess we take tests, a lot of tests already. Hopefully, our experience makes us less anxious about testing. So we should be okay on Wednesday? Okay, so let me continue with the topic of
Just
6.1.
Because she's sure she orders it. Well,
All right, we started talking about 3.1, that is continuous random variable. One of the major change from the from the discrete one is that continuous variable, the probability are no longer summation of probability formulas. It will be integration of the density. So in continuous variable, we have to define something called a density function. For example, in the uniform distribution, the density function is 1 over b minus a. The cumulative distribution function is x minus a over b minus a. The derivative of the CDF is the density function, and that's a major relation here. So we're seeing a little bit more calculus in the continuous probability calculation. The calculation for the probability is integration of the density functions. Enter a little bit integration, a little bit differentiation in its study of it. All right, so this is a density function on the left, a continuous CDF on the right. Derivative CDF is the density function. Integration of density function is CDF function. All right. And then in general, the density function has to be a positive function. The integrating density function on the entire domain should equal to 1. Calculation of a probability should be integration of density function. Okay, and there are a couple examples we tried that given density, we can calculate probability and this cumulative distribution function. Cumulative distribution function basically is a probability formula, and use that probability formula, you can calculate probability as well. Okay, so those are the two that we had in this example. And then let's talk about mean and variance. The mean is calculated by expectation by integration. We integrate x times the probability. So when you want to calculate e of x, now take the x multiplied by the density and integrate it. In the discrete case, we take the x multiplied by f of x, we add it all together. So here we integrate it. We have the integration. The variance is expectation of the x minus mu squared. So you have to have the x minus mu multiplied by the density, then integrate it. Standard deviation squared root of variance as usual. Moment generating function is the expectation of e to the tx. So e to the tx multiplied by density should be integrated. So these are some of the common terms. We might have to compare them with the discrete case so we don't mix them up. So we're gonna apply these formula for the uniform distribution. Number one is the mean for the uniform distribution, which is the average.
Go back to that chart. I was trying to get down the formulas.
Okay. So for example, the E of X in this page is yes. Right, so to determine the mean and variance, if you get a uniform distribution. For the uniform distribution, we have the density function that looks like 1 over b minus a. So you're going to find the expectation of the uniform distribution. Then you're going to integrate. The domain is a to b in a uniform distribution. You're going to have x multiplied by f of x. So it's going to be x multiplied by 1 over b minus a, and then dx. When we integrate, the number is getting out of the integration, and we're integrating x dx. X dx integrated as x over 2. And then you have to put in the integration on the a and b. That's really 1/2 b squared minus a squared. And then b squared minus a squared is b minus a times b plus a. So that's really b plus a over 2. So for uniform distribution, the mean is b minus a over 2. And then over here, you can calculate the variance. Variance, again, the domain for the uniform distribution is x is belong to this interval a to b. So we don't have to integrate infinity to infinity. It depends on the individual variable domain. So you're going to integrate from a to b. And then you're going to have x minus the mean. The mean is b plus a over 2, or a plus b over 2. And then square. And then you have to multiply by the density. And then this again is 1 over b minus a. And then dx. All right, so we integrate this. Integration of a degree 2 question is degree 3. So you have 1 over b minus a multiplied by 1/3 in x squared. Integrated is x cubed over 3. So and there's x minus b plus a over 2 to the power 3. Right, degree 2, we integrate a into degree 3, and we have to put in the integration limit a and b. There. So this is going to give us the final answer. It's actually 12 over minus c squared. That was the variance. And then standard deviation, of course, is the right root of the variance. And that was the try to apply those formula to the uniform distribution. That's the we get variance. And then again, the moment generation function is going to be e to the tx times 1 over b minus a dx, and you integrate from a to b, and that's going to give you e to the bt minus e to the at. That's how we can. You can almost imagine why do we get this. And those are applying this definition to the uniform distribution to get all three. And there's a one-to-one correspondence between the non-general function with our distribution. So next time we see subtraction of e to the t minus e to ta, you should know that's not for uniform distribution. All right. So apply that. For example, if you have a uniform distribution 0 to 100. Then b minus a is 100, 1 over 100 is the density function. And the mean will be halfway between 0 and 100, which is 50. The variance is 100 minus 0 squared over 12. A square root of this variance, we have standard deviation. We can also identify the function. This is the formula for uniform distribution applied to a special uniform distribution. Any question? So a equal to 0, b equal to 100. Using all that, now we have the same thing for actual uniform distribution. Okay, then this example talk about the example that we had earlier, which is this one. So given the density, we want to find the expectation, we want to find the variance for this example, and here are the calculation. To find the expectation, you have to take E of y is y times density of y. Density of y is 2y. So we're integrating 2 times y squared. If you integrate it, it is 2 times y cubed over 3. We plug in 0 and 1. We have to start, which would be the mean. The variance calculation is e to the y squared minus the mean squared. The mean is 2 3. So 2 raised to 8 squared. E of y squared is you take y squared times 2y and you integrate from there. And this is really following the definition. Any question? We're just getting used to how to handle the calculation of mean and variance using the formula we defined in this section. The assignment that we had online, did I assign the first section? Yes. So big, so I haven't really assigned it yet. Okay, so maybe I should do it just. Okay. don't want to be able to talk about it, so after we assign it, everybody can see it on your site on what works. I tried to look at whatever what word has, so it might not be. Should try to relate. um, So this should be making every question start from one. All right, the first question. The uniform distribution question. It's calculating the density function. Uniform distribution from 0 to 5, so the density will be 1/5. The mean will be 0 to 5, the mean will be 2.5. 0 plus 5 divided by 2. The standard deviation should be 5 minus 0 squared divided by 12. So that makes 25 divided by 12. And we can calculate probability. It's a delta. What's the probability? This one was okay, right? Probability of x being bigger than 2.5. The denominator is 5, and numerator is 2.24 is a lower bound. Upper bound is 5, so 5 minus 2.24. And uniform distribution probability can be calculated by the distance given the initial point and term point. That was standard deviation, because we take square root. Take square root of the variance should be the standard deviation. This one, what was the sigma number? Here's a faulty. Oh, the standard deviation is given, standard deviation sigma. So what was the probability of this? Now we have the 1.44. So the upper bound is mean plus 1.44. And lower bound is mean minus 1.44. And then the whole distance is 2 times standard deviation. So this is a standard deviation. You multiply by 2. That's the distance. The distance from the initial point to the terminal is 5. So we'll do any question about this one? Uniform distribution. Do we see anything? There's again a uniform distribution question. I guess these are all uniform distribution questions, except this one. We have a density function. The question is to find the probability more than 115. So you would integrate from 115 to the upper bound, which is 150 of the density function. So you integrate the density function to find the probability. Are we okay? Probability equal to integration of the density from 6. This one you have to find the k first. You integrate the k. You find the derivative, that will be the density function. Then integration of the density function from the lower bound to infinity, it should equal to 1. That will allow you to set an equation to solve for the k. Once you have the k, you can calculate probability. This is a CDF, that's the probability. Okay, so you have to find the derivative and then integrate the derivative to find the k. The rest, they start finding probability and use that one to do the calculations. So try it. If you see any difficulty, do it together. And you can see the integration are going to be applied. Some of the question might look a little bit different than before. This is a homework question that I sometimes put it on the test. Even though we had it in the word assignment, I still see people have a lot of issue with this question. So please try to finish the homework so we can kind of see how the number are related. One of the formula is the expectation. The other one is the integration of the density to 1. And both of these, one equation, two equation will allow you to solve the two variables. Should be solved here. All right, so going back to what we had. So all these topics are applying the definition for EFX and variance effects and probability effects. This is suppose we have the density function, try to find a moment generating function. Any question? Okay, what is this? This is actually a Gauss distribution function. Okay, let's see, for the same function, we can find moment generating function, and then we can find the first derivative and second derivative. Using them, we can find their moment. So the mean equal to 2, the variance also equal to 2. The special distribution, I think it's the distribution. We're going to talk about it in 3.2, the name of different type of density function. All right, so section 3.1 basically define terminology and try to set the tone for some of the common calculation. Given the density, can you find the probability? Can you find the mean? Can you find the variance? Can you determine the moment generating function? So these are what the main idea in 3.1. Another terminology is if you have the density function, you can determine the percentile of the distribution. A P's percentile, we use pi p in this book. Other books use p and p to a number. Notation is okay either way. So P's percentile is pi p, and it's a number in the entire number line of the data value. And lower than pi p, the probability should be the percentage p. So you can see in this formula, p equals negative infinity to pi p integration of density. So this calculation allows you to identify the percentile. So we may be able to determine the percentile when the density is given. So this is our definition way to solve for the pi p. So we want to know what was that percentile? What is the fixed percentile, 80th percentile, to know that number. So it ended up being an upper boundary of the equation of the integration we need to determine. But when you integrate from a number, lower bound of the domain to a number, you put the cumulative distribution function. So if the cumulative distribution function is already given, it's something you already knew, and step that way you put a p, you can solve for pi p. So pi p is kind of like the variable that you need to determine. And for example, look at one of the example questions to kind of see how percentile can be determined given a density function. So here we have, let's determine if the density function is as value of x from -1 to 1, what is the 0.25 percentile? The function is symmetrical, so the 50% percentile is very easy to tell. Let's see, we can graph it. So we have a function that goes absolute value f of x. That's the density function equal to absolute value of x. And we want x to be between -1 and +1. Oh. Right, so that's the density function. That's the absolute value of x from -1 to +1. So that's our density. And so then the area below the density function is probably, so you can see it's the percentile is at 0, right? So if we look for the 50th percentile, so let's say if the function equal to absolute value of x being the domain at 1 to -1, and the function itself is symmetrical. So the area below the function is this. Oh, not good. getting close. Right, so we know that for sure that zero, this is zero. It's 50% on the left, 50% on the right, so we know zero, pi 0.5, 50% is zero. Okay, so now the question will be, what about 25%? Say pi 0.25, how we find it out. And you can see there's negative part and there's positive part. The pi 0.25 has to be on the left, right? So if we want to find the location of it, that means that it's from -1 to the pi 0.25. If we integrate function, which is that's a function. So we were supposed to integrate -x dx, and that probability should be 0.25 because we're trying to find the 0.25 percentile. That means to the left of this, under this curve, to the left of pi 0.25, it should be 0.25. And we should be able to calculate this for pi 0.25. This integration gives us negative x squared over 2 if you integrate x dx. And then we're going to put in lower limit, upper limit, squared. This the pi 0.25 number we're solving. This will put a 0.25. This will be equation that will allow us to solve. So upper limit is negative pi 0. I'll just write pi. Negative pi squared. Well, that sounds so much like the special number of pi. It's negative pi 0.25 squared over 2 upper limit value. Lower limit is -1 squared, so it's minus negative, minus 1/2, right? Plug in -1 for x. It's plus minus -1/2, so it's plus. This equal to 0.25. So let me try to type it. And so the negative, the number we're solving, let's call that a. Negative a squared over 2. Okay, and plus 1 over 2, which equal to 0.25. So solving for the a or I 0.25. So then the negative a squared over 2 is equal to 0.25 plus 0.5. Plus 0.5, you move the 1/2 to the right side of the equation. The whole point of solving is to try to find the percentile. Negative a squared over 2 would equal to 0.75. And then we multiply both sides of the equation by 2, you get 1.5. That was cool. It's minus, right? Oh, wrong. Yeah, that was wrong. We should solve for the a, so that over the plus, I was supposed to do a minus there. So it's negative 0.25. Okay, so then the a squared, and you multiply by 2. Right, so I can just leave it a little bit too hasty. Right, so it should be minus, then it's negative a squared over 2 equal to negative 0.25, and therefore a squared actually equal to, cancel the negative, a squared equal to 0.5. So a actually equals square root 0.25. A equals square root of 0.25 negative, it's on the negative side of 0. Right, so it should be the number slightly more to the left side, right? So that was the process solving for the percentile. In the book, this is a solution. So 0.25 equal to -1 to the pi 0.25 that we're solving. We're integrating that portion of the density function. So integrating x dx, we got x squared over 2. Plug in the number, we have the pi 0.25 equal to the negative root of negative root of 0.25. That was the percentile. By symmetry, you can also find the 75 percentile should be a positive 1/√2, right? Any question? Okay, so this is really example of determining percentile using the density function. Here is one more example. We were given the density function. The question is trying to determine the percentile. This function, the CDF, is already given. One of the situation which will look like is that the derivative, the CDF is a density function. So having the CDF, the process of solving it, you have to integrate this. Now the power is at degree 3, and this is at degree 2. A common way to look at it is to apply chain rule. So it looks like the derivative of the exponential part equal exactly what we have here. And it's possible to figure out the antiderivative from the density function. So why don't we talk about this? If you have the CDF already, then the CDF can give you a quick formula to identify the percentile. For example, the lower percentage of the 30% percentile would equal to 0.3. So the capital F of X is a probability. So probability to be below pi 0.3 is 0.3. So then we get this equation, you plug in pi 0.3 into this equation, you get 1 minus e to the negative pi 0.3 over 4 to the power 3 equal to 0.3. That equation allows us to solve the percentile. We can solve the percentile for pi 0.3, which equal to the 2.84. The algebra part of it is a solving process, but it's not too complex once we already have the CDF. Any question? That example. This here we have another probability density function, and then again calculating probability is integration. To find out probability x bigger than 1, you integrate from 1 to infinity, integrate the density function, and then we get a probability. To find the moment generating function, you have to integrate e to the tx times the density function, which essentially have the exponential integrating of exponential function. And then the antiderivative is not too hard to get to once we factor some factor out. But here we have the moment generating function, which allows us to again determine the moment. The mean will be the derivative, first derivative evaluate at 0. The variance is the second moment subtract from the first moment squared. So then some of the problem that we had about understanding the moment generating function still apply, except the calculation now involve more integration. Any question? When you actually sit down to do some calculation, you can see many things that we learn in calculus is fine here. For the same question, we can integrate the density function to get the cumulative distribution function. So for example, the density function is e to the negative x minus 1, defined from -1 to infinity. So the f of x is integrating from -1 to x. Lower bound is a natural boundary of -1. Upper bound is at x. You integrate the density function. Then the antiderivative involving bring the e to the -1 to the outside, integration e to the negative w is negative e to the negative w. All right, and then the CDF can be decided once the integration is clear. Any question? And having the CDF is very convenient. That's why sometimes people will try to devise it, and then once you want to determine the percentile, the CDF is very useful. The equation can be derived without integration, because integration has already been done in the calculation of CDF. And that's the 3.1. Any questions? Okay, so basically the 3.1, the midpoint, it provides relations. and try to differentiate the relation from the discrete version of it. And we did so much practice of the discrete probability. Now we have to review many of the skills that we had from calculus. So we might have to bring out our formulas for integration. Question. Are we okay? We don't have a minute. Is it okay? We'll talk about 3.2. Yeah, all right. Because I've always felt like the class time is not enough. Basically, this is the chapter 3 does not have a lot of sections. We only have 3.1, which introducing the probability density function, how we calculate probability if we have a continuous situation, how do we find the means, how do we find variance and homogeneity function. So that's the focus of 3.1 is set up those relation and definition. And then as usual, now that we introduce the idea of continuous distribution, 3.2 and 3.1 bring out some of the most common continuous distribution. So what are the most common distribution? 3.3 focus on normal distribution. I think you all have heard of the normal distribution, right? You heard normal distribution. In elementary statistics book, we normally do the normal distribution with a normal distribution table. So statistics handle the calculation from the table, and probability handle the calculation for probability using the integration. So we kind of bottom line from doing things massively with calculus approach, and then we slowly moving into the statistical setting when problem and scenario are solved with massive data. So you have table of numbers, like we have Poisson table, binomial table, and then later we have gamma distribution. There's also table to go with it. So there's always two different side of ways of just doing things. You use the integration derivative and the calculus version. And that was the main idea in probability, and in statistics, we handle everything with the massive understanding of data. So getting return of these. So 3.2 focus on the exponential distribution and gamma distribution. 3.3 focus on normal distribution. I suppose normal distribution are the easier session. Okay. So let's talk about the normal distribution. We have like 15 minutes left of the class time. Hesitated what were we supposed to do? Right. So let's talk about the common type of continuous distribution. There are more continuous distribution. There's also more discrete distribution, but we can only cover so much. Let's see. Two examples. Okay. The title of 3.2 is called exponential distribution, gamma distribution, and chi-square distribution. They all follow similar things. In that section not, I intended use. I started out a little less here, so. Once in a while, I try to go in a different way of explaining things. I think I changed the way I explain things here. So 3.2 focus on exponential distribution, gamma distribution, and chi-square distribution. Starting out with most simple one, exponential distribution. So what exactly is the exponential distribution? The most common thing that exponential distribution can describe in waiting time. So it's connected to the 2.7 that we mentioned. 2.7, we have Poisson distribution. For Poisson distribution, the only parameter is the average number occurrence, which is being called lambda. So let's say X follow lambda distribution. which means, this is something we have, on average, there's lambda of these happen in a certain amount, like certain time period. So the probability for Poisson distribution is lambda to the power n if you are calculating x probability that n times something is occurring. So lambda to the power n over n factor 2 multiplied by e to the negative lambda. That's a Poisson distribution probability formula. Then Poisson distribution is discrete. So when something occur in the discrete version, and they don't always occur, so it occur here, and you wait, and occur again, and you wait, and then occur again. So that's when things are in discrete form. So now time is different. Let's use W to represent the waiting time for one of the Poisson distribution, Poisson variable to occur. So let's say we wait W time for it to occur, and we want to calculate or figure out a way to model this W. So we're gonna try to calculate what is the probability the waiting time is less than X. Right, so what does that probability means? When you see the waiting time is less than X, that means between the time 0 to time X, there's a 0 occurrence because you have to wait so long. The waiting time W is less than X. So between 0 and X, there's 0 occurrence. So how do we calculate the probability there's a 0 occurrence? It will be e to the negative lambda. That was our probability, right? E to the negative lambda for the probability of 0 in the Poisson distribution. However, if your time frame is 0 to 1, then the probability of 0 occurrence will be e to the negative lambda. But if your time frame is 0 to 5, it will be e to the negative lambda 5, right? The average occurrence is doubled. So the actual lambda for 0 occurrence between 0 to x is e to the lambda x, right? The mean has to be multiplied by how long the time that you are identifying. So this probability is 1 minus e to the negative lambda x. We end up having a probability for what is the probability W is less than X. And a probability of variable less than a certain X is the definition for CDF. So this is a cumulative probability for continuous distribution. That's exactly the probability we're looking for CDF. So the definition for CDF of W will be f of x, which now have a formula 1 minus e to the negative lambda x. That was our probability formula. Our probability formula is a CDF we're looking for because we're trying to find probability below the variable x, variable waiting time below x. We got that formula. That's our CDF. And once we have our CDF, derivative of CDF will be the exponential distribution. All we have to do is find the derivative. Derivative 1 is 0. Derivative e to the negative lambda x is e to the negative lambda x multiplied by negative lambda, right? So we would have negative lambda times negative 1. That's lambda e to the negative lambda x. That is the density function for exponential distribution. Any question? Oh, you okay? All right, so that's the so then we are using a new parameter in the exponential distribution. We certainly do not want to use the same variable as in the exponential distribution. Another thing is the number of occurrence and the waiting time are reciprocal of each other. Because if the number occurrence is 5, within 0 to 5, 0 to 1, if the occurrences 5 occur, like in 1 unit time, you have on average 5 occurrence. So how much time do you have to wait on average is 1 over 5, right? So the waiting time is less when the occurrence is more. So between the average waiting time, we use theta. Okay, so theta equal to 1 over lambda is our average waiting time. So that changes our formula. Our formula for the CDF is 1 minus e to the negative lambda theta lambda x. Now lambda is 1 over theta, so we have negative x over theta. also, and theta equal to 1 over lambda, lambda equal to 1 over theta, reciprocal of each other. So the density function will be 1 over theta times e to the negative x over theta. That's the official density function for exponential distribution. So if x has exponential distribution, then the waiting time will be 1 over the lambda, or the theta will be the average waiting time. Okay, so for example, let's say some variable x have exponential distribution, the mean equal to 20. By 20, we mean theta equal to 20. So with that, what was the density function? What was the CDF? And then we were able to calculate the probability x less than 18. And this relation between the Poisson distribution and the exponential distribution, we have to try to connect them and yet differentiate them. And exponential distribution model the waiting time, Poisson distribution model the number of occurrence. So Poisson distribution is discrete. It counted 1 for 1, occur once, occur twice, and so on, right? Waiting time, you wait for 1 hour, wait for 5 minutes, so waiting time is a continuous variable. Now, suppose we got something that has a mean of 20. So it says theta equal to 20. Now, let's write the PDF and CDF. The PDF would be the density function for fx equal to 1 over 20 e to the negative x over 20. Exponential distribution have exponential function in there. And then the cumulative distribution function is a probability, and that's the probability that this one. So it's 1 minus e to the negative x over 20. It looks kind of similar yet different. So that's the CDF and PDF, and then let's calculate this probability. As usual, the calculation of the probability, there's 2 ways to do the calculation. You can calculate using this one, or you can use this one. Now, if you use the density function, this calculation has to be from 0 to 18. You're going to integrate your density function. This calculation dx. So that's the calculation for the probability. Or you can use this one, because this one already representing probability of the random variable to be less than x. Now you have less than 18, all you have to do is put in 18 into this. So you can calculate this simply by f of 18. Because this is the integration of this, right? You already have the integration done in your CDF. You can just do 1 minus e to the negative 18 over 20. And that will be the answer. We put it into the calculator. If you did the integration here, your final integration is upper limit minus lower limit value. It will be the same thing as that. So supposedly, if we do have the CDF for probability calculation, the CDF is always more convenient than the integration of density function. Because if you integrate your density function, you will be repeating the same integration that you did with the CDF calculation. Any question? Are we okay? Right, so sometimes we revert back to the integration of density because that is that's the thing that we have to do. But most time when you have the CDF, we prefer using the CDF. And that would be first example. Okay, so that was the calculation. The density function is on the board. The calculation of density can be done both ways. You can integrate the density function from 0 to infinity. Exponential distribution is waiting time. Waiting time cannot be negative. So your domain is 0 to infinity. And or you calculate, that's essentially the CDF. So you plug in 18 into your CDF, and you will be getting the same answer. So in this presentation, it looks like we're doing the integration, but this integration will give you the same answer that you would get from your CDF. So that's the calculation of using exponential distribution function formula to calculate the waiting time, probably that we wait less than 18 And this is a comparison between the CDF and the PDF of the exponential distribution. It is a distribution. We have e to the negative exponent. So in the density function is a decreasing function. And also because below the density function is probability. So the area below the density function supposed to equal to 1, right? So of course the function cannot be increasing. If you got an increasing function, how do you guarantee below the density is 1, right? You're gonna get bigger and bigger, so it's decreasing. On the other hand, the CDF is probably below a certain number. As we go forward, to be below, the probability gets more and more. The highest value for any probability would be 1, right? It's 1. You start with 1, start from 0. That's how it is for all CDF because it represents the probability. In the formula, there are a couple other things that are being referred here. Number one is to calculate the median. Median is a 50% percentile. So if this is the CDF, 1 minus e to the negative x CDF. So if the median use m, then 1 minus e to the negative m over theta should be 0.5. And solving that m, you can find the location for the median. And then for example, m would equal to, you subtract 0.5 and you got 0.5 equal to e to the negative m theta. Negative m theta equal to logarithm 0.5 and then multiply by theta, we have the formula for m. Then you can try to graph it once you have the location for m. Let's say the theta equal to 5, and then there's a calculation for the median. So median is at 3.466. All right, suppose the average waiting time is 5. This is again presenting one comparison. In statistics, median and mean supposed to have something similar. They're both representing the middle, right? The middle. Mean is the average and median supposed to be the middle. And you can see right here, the mean is 5, theta equal to 5, and the median is 3.466. So we can see that clearly the mean is 5. 5 is bigger than 3.466. That's the data is right skewed. Median is over here, mean is there. Mean is bigger than the median, so it's right skewed. In the symmetrical data set, if data distribution is symmetrical, I mean left side and right, there's definitely no symmetry, right? This side is here and that side is the shape of the distribution from the density. You can see it's not symmetrical. Definitely right skewed, having a longer tail on the right side of the distribution. Comparing the median and mean also indicate the same thing because the mean is way bigger than the median. Any question? Are we okay? So occasionally I want to review statistics a little, even though we're talking about probability. All right, what if we want to calculate probability x is bigger than x? The calculation will be lower than x, bigger than x, they're opposite. The capital F of x represent probability lower than x. If you do 1 minus f of x, you have the probability to be higher than x. However, in the exponential distribution, the probability lower than x, the fx is 1 minus e to the x over theta. So 1 minus when a minus 1 is cancel. So probability to be higher is e to the negative x over theta. Any question? All right, let's see the time. We see similar things. Do you remember geometric distribution? The probability to be a higher than a number is q to a power, right? And this also has something similar to this. When you are looking at the upper tail, it shows as a really small value, and with a single formula. Okay. And we're probably not gonna assign the homework so soon, but this is an example where exponential distribution are being applied, and then this is a very popular model for waiting time. Customer waiting for something, waiting for a mail, or a lot of waiting time model. We very commonly using exponential distribution. It's time. We'll talk about more example next time, but in the meantime, please get ready for the test on Wednesday. So you don't have to worry about this, but I want to mention this so we have more time next time. I'll see you next time. make sure you get ready, see Wednesday. I feel like I'm trying to like move forward, inching in whenever I can.